Perfect. Okay. Let me hide this thing on the right. Perfect. So let's go. Let's watch everything. Okay. So hello everyone again. Many of you are also yesterday, so we got to know you. And for people who may be new, I mean on Zoom maybe or other places, welcome. Today we want to talk about transformers, continuing the talk we had the past 2 days, starting from basic neural networks, then to convolutional networks, and then to RNN. Now we want to extend it one step further. Let's see. Should I remove this thing? Sorry. Sorry. Okay, perfect. Okay, let's go. So what did we see the past 2 days? We first saw again a recap. Okay, I know this is too repetitive for you, but I'll just briefly go over it. We saw about the deep neural networks. There were networks that you put data into. We had some hidden layers that transform the data in a sense, and then you had the output layer. The output neuron could be only one that would output a number, for example, or could be multiple neurons that would help in classification. Each of them could be, for example, the probability of a certain class. I think it's close the door, right? And some voice I think is coming from here, but we can't do much about it. I try to speak louder. So yeah, there are multiple. Yeah, have bunch. Anyway, so we have multiple output neurons. Good idea. Each of them could be related to a certain class, the probability of a certain class. For example, if you want to classify between if a text is referring to being angry or sad or happy, each of them can be neuron with its own probability. We will actually cover it a bit in this lecture. Then we saw convolutional neural networks. I won't go over it because you have already seen it yesterday and it's not related to our topic today. But yeah, so we had an image consisting of pixels. It could have been multiple channels, and then you had several convolutional and pooling layers until you transform the image into a format that is recognizable by the fully connected layer. Importantly, yesterday we covered time series. We learned that these time series are data that are measured at regular intervals or step by step. It could be numerical data such as temperature or heartbeat or stock prices of the companies. And importantly, we said it could be also the written text. Each written text could also be formed as a time series because the words come after each other and each of them represents a specific time in history. And we learned we can either do classification. For example, given a time series, classify if it belongs to a certain class or not. In text, it could be classify if a text belongs to a certain class or not. And we can also use it for prediction or forecasting. For example, predicting the temperature of the next day, or predicting what the heartbeat of the patient would be, or the stock price of the company next hour, or completion of the text as it's used in autocomplete interfaces. So we learned about time series, and we saw that recurrent neural networks could help. So sorry, we saw these networks have a recurrent component in which if you unfold it over time, each neuron takes one input from the time series and outputs a hidden state, and also outputs something for the next neuron. So an internal state is updated over time, and this internal state helps the network to identify patterns in the data and be able to better follow time series data. So this was the original whole idea behind RNNs, as we saw. We saw they have some limitations. For example, because in the back propagation of RNNs, they do gradients using the chain rule, as you may know from derivatives from calculus. These derivatives are multiplied by each other. And if they are less than one, if you multiply a number less than one multiple times by itself, it would be less and less and closer to zero. This would help to all gradients be set close to zero and thus no important updates in the model. This can lead to several problems. One main problem is that data from early steps of the sequence could not be represented well in the ending of the sequence. For example, if you want to have a text completion interface and the text is I'm from France and then some stuff and then I speak and you want to complete it with the word French, for example. If the I am in France part was very, very early in the text, the model actually forgets it because the vanishing gradient problem leads the gradients of that moment to be set to zero, and that is not very helpful, and it can lead to incorrect or not so correct completions. People have done several things to mitigate this approach, as we covered yesterday. I mean, this is not the focus of today LSTMs, but we build upon RNNs actually. But just as a recap, we also start LSTMs, which are the architecture that have a steady state that runs over time, and we modify it using forget gates and input gates. So there are mechanisms that help the model to forget or to add new inputs on demand by the amount that it wants. This architecture helps a lot in improving the performance of RNNs when working with long sequences. However, it's complex to train usually. So it's not very easy. It has a lot of parameters, and especially in long text, it's super complex to train. So with that said, let's jump into what we want to cover today. The general idea, so all the models that we saw could be somehow classified as a general idea of a sequence-to-sequence model. What's that? In a simple RNN, we had multiple inputs. This is actually, this is not a new model. This is a design architecture of models. I'm not covering the new model. It can be in a simple RNN, but I'm talking about the general design architecture of models. What's that? In RNNs until now, we had several inputs, and we had some data sets and a final output that we use for our prediction. However, a more general idea could be a sequence-to-sequence model in which we have the input here, and we have some RNN cell or any cell called encoder. The encoder cells have their role to get the input, which is the raw time series that we collected, and transform it to a format that is somehow useful for the model, for the computer to understand. So this is the role of encoder. Then this is the whole encoder part, which is just simple RNN cell. Then the final encoder output would be transferred to the decoder. The decoders are again the RNN cells, but here, these Y1, Y2, Y3 are the hidden cells of those RNN. If you remember here, each RNN has also a hidden output, right? So the hidden output, you can also get it from the RNN. Or the output, I mean, not talking about the hidden thing, but any, like the output of the model. You can use the outputs of the model as a transformed version of the input. So this is the general idea of sequence-to-sequence models. You input your model to a set of RNNs, you use the last state, and again pass it to a sequence of RNN, but here it's vice versa. We don't want to pass input and get the output, but rather pass the first input and get the output from the RNN. Here, the only output that we care about is the output of the last input. And we care about inputs, but here, we care about all the outputs. So this is the general idea of a sequence-to-sequence model. What it can be helpful for, people initially use sequence-to-sequence models as a means for machine translation. How does it do? Imagine we have an RNN strong enough that can do machine translation. Here, we can input a sentence, for example, just be pasta in French. Each of them can be a word. I imagine we can somehow convert words to numbers. We will cover it in NLPB, but we can somehow convert it. And the role of this encoder phase is to convert all sentence pasta in a format that is parsable for the model. So the output encoder here is a big vector that somehow condenses the information that means I am parsa or je suis pasta. And then we input it to the decoder, and here the decoder outputs word one by one, which is, for example, the English translation. For example, it can here in the first, it can output a number corresponding to the word I, the second corresponding to the word am, and the third corresponding to the word parsa, for example. And it can translate it for us. So this is the general idea of sequence-to-sequence models. If we train it in such a way, it can output the task for us, and it has been successful. Yeah.
Struggling with the representation.
So yeah.
X1 is related to Y1.
So it could not be exactly one-to-one, because for example, in translation, the order of words can change.
What I mean, building neural network, neuron one has X1 and Y1, well, that's not really struggling to.
Oh yeah, X1 are not neurons. Here are input, or just numbers. I mean,
then get presented to the network.
Exactly. So imagine we have a dictionary that each word has a numerical value, for example. For example, I'm just oversimplifying because that's a whole study on its own to how to find representations. I will cover in the NLP because it's not useful if you just assign a number for each word. There are ways that you assign meaningful numbers to each word. I will cover it. But Yeah, imagine, for example, I is the number 0, am is number 1, and parsa is number 2. Like they are represented like this. You just pass the numbers into it. And the model is trained to translate. Yeah.
So then we've got the flow, it's got C1, C2, 3, and then X to the fourth word.
Exactly. So the last one somehow includes information from all of them. That's the idea. Here, the output of this includes information from everything here. I mean, it has the vanishing gradient problem, I know. Yeah, and that's the challenge that we are covering. But yeah, exactly. Yeah, here. So here, we input the word, the encoder encodes it step by step, and the final state of the final encoder is the representation of the whole sentence. I mean, I'm talking about sentence, but it can also be other time series data. And then you pass it into the decoder. Decoder decodes it step by step. So this is the general idea of sequence to sequence, or sometimes called encoder to decoder models. That's very important in understanding also transformers architecture, because it's generally based on the same idea, which we will cover it. But here, yeah, they are simply RNNs. Each of them is a simple RNN cell. Each encoder is a simple RNN cell, like here. These are RNN cells. So here it's just normal. We don't have encoder and decoder in a sense, but here we just separated them semantically. It's not something changing the architecture. It's just another way of thinking about the RNN. Some of them are encoder and some of them are decoder.
Okay, so here there are 8 units.
Yeah, exactly.
So
Yeah, I mean, yeah, inside them are also things, but yeah, 8 RNN cells. Yeah. Here are 8 RNN cells. We just semantically say these for our encoder and these for our decoder. This is what we define. They are not different in architecture at all. Like the encoder is the same as decoder here. Yeah. So that's the idea. You use sequence to sequence models to, for example, you can use for machine translation, which was used a lot, like input a French sentence and get an English or other task. Yeah.
So here we get go through the encoders, we have a sequence of numbers that represent words.
You mean here in X1, X2?
Like at the output of encoder X4.
Oh, here.
Yeah. So we have a
Here we have a big vector that it's usually not interpretable. It's usually a mix of numbers that only the model understands. We can't like see the vector and see what was the sentence.
so the decoder is to translate that vector.
Exactly. So we condense all the words into a single big vector that somehow has the meaning of the word, and then the decoder's role is to decompose it into words. This is the general idea. I mean, in the very basic information. I'll talk about attention models and how they help, but yeah. So this is the very basic idea. I will also cover it later, but until now, any questions again? Yeah? Maybe a bit louder because this thing is very familiar. Oh, okay. So the question was, I think, does the decoder start from decoding a certain word or not? So here the representation is a mix of all these words. Here the decoder does not have any idea about the extent. The decoder only sees a very big vector, a multi-dimensional vector in a multi-dimensional space, maybe 100-dimensional, 512 dimensional, something like that. A very big vector that has somehow, how should I say, has a representation of the whole sentence, and only decoded by that. It doesn't have any idea of the original word. Converting the original word to a good format is the job of the encoder, and the job of decoder is to decode it. It's somehow similar to how real encoder and decoder work in like logic design or this kind of thing, right? You usually encode analog signal to some format and then you can decode it. Like this is quite similar. They're neutral. Let's go for more. Perfect. Okay. So now we want to extend upon this way of thinking about RNNs and introduce some new methods. Which university is this? APFL. Okay. So could you tell me which parts did you look at to identify this? Rolex? I guess maybe you would say the lake, or no? Did anyone look at here to identify what's the name of this university? I don't think so. Or maybe look at there. I don't assume. I assume most of you looked at here. Just, you usually scan quickly by your brain and you directly looked at there. Or maybe to the lake. For example, I first looked at the lake and said, wow, that's similar to Lake Geneva, so it should be EFL. Or for example, I don't think people have do this here a lot. Maybe I'm wrong, but you can prove me wrong. So yeah, our brains usually pay attention to certain parts of input. This is usually how our brains work, right? This was originally the inspiration for also researchers to find if we can somehow train the models to only pay attention to a specific parts of the input. So you remember here, imagine if we had the outputs of all these encoders and decoders, and the model at training time or at inference time could have picked which parts of the word it can pay more attention to. Why this is useful? Imagine the same example. I am studying in France, and then you later say I speak and it wants to autocomplete French. Which word do you think in the sentence the model should now attend to? It's France, right? To identify the language. So if the model is trained that when it's asked about language, it should attend to the country names, it would help the performance of the model to be very better. So this was the general idea. Our brains are usually trained this from our childhood without us knowing, but we should do this explicitly for the models, right? So this was the general idea behind attention mechanism, as they say. As you remember, until now, the final decoding step had to represent the whole word of the encoding phase, right? Here we have information loss, obviously, because when you condense a whole sentence into a vector, some information are lost. I mean, this is very basic, right? You can anytime it's the whole idea of compression and everything you may have learned in algorithmic course, right? When you compress the whole thing into a single vector and then decode it, some information is lost here. So it could have adverse effects on the quality of the translations. And actually, it has shown to be the case. So RNN models for translation maybe work good for simple sentences such as I am parsa when you translate it, but when you give a document, they're usually a struggle. Because how can they compress the whole document into a single vector? It doesn't make a lot of sense. So the translation is not very high quality. The initial idea here, we are not skilled at transformers. This was the initial idea, is that, okay, we can have an addition to this architecture, helping it to attend to the different inputs in the sequence. What does that mean? Here we have the same architecture again, but in addition to this, in the input of each of these RNNs, there is also a linear sum average, weighted average of all the outputs from these RNNs. So maybe this picture is bigger. So here, imagine the same thing, but in addition to what you have, in addition, don't remove anything here for now. In addition, imagine each of these decoders had also the input is summed with a weighted average of the outputs of this RNN. What does that make sense? So the weighted average actually is a kind of, because in weighting average, you have more weights for certain words and less weights for other words. So you can choose which word do you pay more attention to and which word less. It's the general idea. So imagine each of them has an output. For each of the decoders, you use a weighted average of the outputs of the decoder and add it to what is already input to the decoder. The idea is that here we removed somehow the problem of the information loss. Why? Because we not only have the condensed version of the whole sequence, but also we can directly add output of each encoder that corresponds to single words, which makes a lot of sense. Because in that case, the decoder not only sees the general compression, but also can attend to a certain token by increasing its weight in the training phase. Was it clear? Any questions? Was the general attention mechanism clear and everything? Yeah. Yeah. I mean, weighted sum, not weighted average. Maybe I said it wrong. You don't usually divide, but yeah. So yeah, all of them are matrices that you also have in your formula, and you just do it in Python or any other library that you use, and they are also updated in the backpropagation. So the weighted averages, the weights for each of those things are also matrices that are updated in the backpropagation. That's the general idea. So by doing the general optimization and general training algorithm of the neural network, the weight of those matrices are also updated. But that's true that maybe you would say, but there would be a lot more parameters, so we need more time to train and everything, and that's true. Yeah, we need more time to train, and they're usually more like they consume more memory, consume more space, and things like this, or more time. But yeah, in the end, imagine, yeah, we are just adding new matrices to the loop, and all of them, sorry, and all of them are again trained with again trained in the loop, and are their weights are updated via backpropagation. Yeah. So let's go. If you have any questions. So as we saw here, in the general idea behind the initial attention mechanism that was used, I think, so this was, I think, a bit on topic like maybe 2015, 2016 or so. People used it at that time. So yeah, here the idea is that in addition to outputting the last encoder into the whole decoder, we use a weighted sum. I mean, I use weighted average, but weighted average is not a very good word. So weighted sum, and add this, here you can see the plus icon, add this to the input of the decoder. This helps the model to look at all the encoder hidden states, and thus it can attend, as they say, to certain tokens in the input. I mean, by tokens, I mean data entries. Token is the NLP word, but they use it there, but you can just replace it with any number in the time series. So, and how this is usually done? So, yeah, I mean, I talked about, yeah, you can have the weighted sum and everything, but in fact, how the initial authors, I think, have done that is it's a bit more fancy. So they have a very simple, fully connected network here. It's not just the weighted sum. We have a simple fully connected network here, and the softmax. I'll talk about softmax. It's just for now, consider it something like an activation function, but I will talk about that later. I mean, for now, consider something like sigmoid. It's not different, but I'll talk about that later. And then you sum them and multiply, and then you input it to the decoder. So it's actually a bit fancier than just the very normal weighted sum, but that's how it's implemented in practice because it enables like more fancier attention rather than just a simple weighted sum. But the general idea is something like that. So each of the outputs of the encoder, here we are showing one of them actually, goes to, so I mean, here it's not only one cell, there are four of them. As you can see, C1, C2, C3, C4. It's just for oversimplification. They just did this. There are actually four of them. For each decoder, you have one of these gray boxes, which gets input from all the encoders, but outputs them to a single decoder. Yeah. Perfect. Okay, any question until now? All right. Yeah.
Zero.
Oh, where's that?
No.
Oh, is the initial, okay, yeah. Maybe I should have said this. So here, I think it's actually output from here. I don't know how they do this here, but good question. Here it should come from here. I mean, still in the original or in the original approach that we saw here, you can just output S0 from the output of the last encoder. But you can also pass an initial amount that is not related to the encoder to the last encoder at all. But I don't think they have done it here because they already output H4, which is the output of the last encoder into the loop. So I don't know here what they were actually in this picture. I don't know. But you can use the output of the last encoder or just a random value. As far as I know. I think, yeah, if you just add attention to the normal RNN, you can just use the output of the last encoder. You can also use the random value. It doesn't matter because it's still due to the some weighted sum, the output of the last encoder is contributing to the first decoder. So even if you don't pass it like this, even if you pass it like this, during the attention mechanism is already involved. So yeah, I don't think it matters a lot, but actually that's a good question. Maybe this picture is not very clear. S0, I don't know where it comes from. It's like a bit weird. But yeah. Yes. All right. Maybe I can check this website later. I put the links for actually all the pictures that I brought from different websites. So I can check the website. Maybe they wrote website zero here, but yeah. Okay. So here I provided a quote from one of the authors behind the very famous Transformers book. They say that the main idea behind attention is that instead of producing a single state for the input sequence, as we just had. Previously, we had, okay, the whole RNNs were just compressed into a single state. The whole idea is that instead of that, the encoder outputs a hidden state at each step, and the decoder can access it using the weighted sum. So as you can see here, this is another interface of showing that. So here we have again, this translation task. The four words are inputted here to the RNN cell. And okay, they are connected to each other, obviously. Each of them outputs, they're encoded, right? Each of them outputs a certain state or output. And then for each RNN step of the decoder, a weighted sum, I mean, a bit fancier with the feed-forward network, but yeah, a weighted sum of these states are inputted to that RNN step. And the output is the word that is the correct translation. So as you can see, I think it's German. So the translation is provided. So this is this is another visualization in that book. I took it from the book. This is actually a nice book if you want to do it later for NLP transformers. I usually advise to read this book. I think I've told 100 people until now to read this book because I really like that. So yeah, this is a generally nice visualization of how the encoder and decoder work if you add attention to the RNN. So if we didn't have attention, we didn't have this whole thing here. No, we just output here to here, and that's it. We don't have any input from the address. So yeah, we just has the state 4 to the RNN cell 1 of the decoder. That was the whole thing if we didn't have attention. And actually, when you train this, you can train an attention model on top of an RNN and visualize the weight of these connections to see which models are which words or which entries are the model attending, as we just said. And people have done this. For example, here is an example of a model trained for translation. The translation is the agreement on the European Economic Area was signed in August 1992. So this was the translation and also the French version. And they saw which word does the model attend to for each input. They just actually show the value of the weights of these links after the inference. So for example, you can see here echo is like with agreement, the attention is higher. And most words, okay, you can see it's very obvious because the order is the same, but here that the order is not same, you can see the model has recognized it. For example, economy, here the position is different. Here actually in French it's economic European, but then it's European economy. And the model has recognized, as you can see here, European matches with European and economic matches with economic. And yeah, so as you can see, this model is actually successful in finding relations between words in the after training, and can and yeah, because of this, when you are applying this model for a real translation task, if you put this sentence to translate, it doesn't need to only rely on the compressed whole encoding phase, on the complex output of the encoding phase. It can directly attend to a token. For example, if it's after, for example, economic area was signed in, and then it knows which word you should attend to, here it maps to auth. So it can directly just use the translation of the auth from what it has learned and output August, which makes the model way better in translation. So this is the general idea of attention. Any questions?
This is directly reading the attention matrix.
Exactly. I mean, here, actually, this is visualization of the values of this. So, for example,
so the size of that to be, what if that attention blocks to be the language.
Yeah, exactly. I mean, we'll cover it in NLP. What you usually do, we have a vocabulary. We call it vocabulary, which is the possible set of words that you can do in a language. And yeah, that's actually has some complexities that we will cover in the NLP week, specifically how you do it in NLP. I mean, for now, you can consider the whole language is just these words, and these are just numbers. Because ultimately they also convert to numbers, but that's a different story. But yeah, for now, consider this is the whole. Well, this is oversimplification, but for now, you can consider this.
So here you have to integrate it. It's easy to think about.
Yeah.
General transitions or what.
Yeah, even more. So the idea, because I mean, we will cover it, but the idea is that you don't use individual numbers, but rather all numbers are usually values in highly dimensional space, and they have relations. For example, we will see in the conversion of words to numbers, they are usually converted to a vector, and the vector has semantic meanings. For example, if you take the vector of Switzerland, if you take the vector of Switzerland, you remove, I think, yeah, that's actually a nice thing. So you take the vector of Switzerland and the vector of Germany, and then the vector of Bern and the vector of Berlin. The differences between the vector Switzerland and Bern is equal, somehow almost equal to the differences between the vectors Germany and Berlin. This should be the characteristic, you know. So the vectors in this dimension have meanings. It's not just random words, and that helps them in translation. So yeah, they are the specific things in LLP. They are just not random words, but yeah, you're right. So here we are oversimplifying everything.
It's just understanding the dimension. So this is clear enough. It's the useful part of that matrix.
Yeah. Yeah, exactly. In reality, it's much bigger, but in reality, it works. So in reality, attention was successful, more successful than simple RNNs. Exactly. And okay, do anyone has another idea why attention based on what we learned? In addition to the improved performance, what could be another benefit of the attention mechanism based on what we see? What do you mean? Oh, yeah. You can also have, but I mean, even if you do this, because these models are bigger in size because they have the weight matrices of the inputs, and they're usually bigger and harder to train. Ultimately, still transformers are harder to train than RNNs usually. So I don't think you get a lot of benefit from that. It's mostly so yeah. One good thing of RNN is that they take less memory. That's a good thing. I think also Peter mentioned yesterday. So RNNs could be somehow useful for small devices. But yeah, you're right generally. But what I wanted to say is the interpretability. Here we have some kind of interpretability of how the model is doing. We can see that, well, the model has attended to this token, so this was why it outputted this. So if our model has the behavior that we can't understand, if we visualize it like this, we can see for a certain output which tokens it has attended to, which inputs it has attended to, and thus we can somehow debug the model. So it's a, I mean, it's not a full interpretability, but it's something in that direction. It's at least better than when you compress everything in a single vector in RNNs. Yeah.
So it's shown to be not just go to, but there are some techniques when you apply some ways that you can get to.
Exactly. Yeah, that's what I said. This is just something in direction of interpretability, but that's not enough. So you can't just say, oh, I have a transformer model, so it's explainable. This is not the case. Never just say, well, I replaced my RNN with a transformer, so I can say I do explainable AI. No, this doesn't make sense. So yeah, exactly as you said. Perfect. So if not any question, any downside that I mean, we covered it actually, but so you have some downsides that came to mind. We talked about some of them. For example, they are usually bigger and more difficult to train. But also anyone can come with another downside of the whole approach. I mean, not just attention, but also RNNs and everything that we saw. Do you think one downside of the whole RNN? Imagine, and also as a hint, imagine we want to train it on very long text. Okay, here we don't have the vanishing gradient problem, right? Because we can attend to any token in the sequence. We don't have the vanishing gradient problem. But do you think any other disadvantage of RNNs if we input very long data? Maybe, yeah. Oh, what do you mean?
Because
Yeah, certainly. Yeah, being very big matrices that usually don't fit enough in the memory is a downside. Exactly. So that's one thing. But actually, that one is not something that it has been fixed because, and you can see it because still transform model are very big, like GPT is very big, and so that one is still unfortunately not fixed in the literature. But yeah, That's a very nice thing. So here actually we know because the RNNs are sequential, right?
So there's no.
But here we don't need it. Like for simple RNN, we don't need. For transformers, we need, and I will cover it. But here, ideally, we don't, because the output of this also includes data from the previous one. So it's not, for example, state 2 is not only about R, but it's about transformers R, in a sense. I mean, it's indirectly, yeah, I agree. And you can add also positional embedding to make it better, but that's something that I'll cover in this transformers because what we do is related. Okay, what I want to say actually, and the book said, is that for long text, you can't do the processing in parallel because you need to start from the first cell, and go for that. And for example, if you train it on a book or long corpora, as for example, GPT is now trained on the whole internet, so it's a very, very long text. If you do it like that, it's very inefficient to train because uh, you should first do the RNN cell and the output is used on the second one, so you can't train them simultaneously. So one idea that also came with a lot of disadvantages that I will show you how to fix that was that let's remove the recurrence altogether. I mean, that may seem crazy, but let's remove this whole connection and just remove the RNN. Okay, issues. Why are we doing this? Like we introduce everything to an RNN, but they said, yeah, why not we keep the attention but remove the RNN now? We don't need the recurrence anymore because the input can attend to every token in the input. The output can attend to every token. Why do we need recurrence at all? So this is the idea that the very famous paper you may have heard of. Attention is all you need. This is actually a very, very famous paper, like cited, I think, multiple million times or something like that. A very famous name actually in the field. Attention is all you need refers to we don't need recurrence. We only need attention to have great models. And they did this. What they did is like this. So they replaced the whole thing. They have no argument here. They are just four. Okay, here four because the sequence length is four. But we have four feed-forward neural networks. Each of them gets an input and attention, like a weighted sum. Then the states are outputs of these feed-forward neural networks. And then in the decoder, we have again the same thing. So the feed-forward neural networks attend to the input the states and output the words. So you remove the RNN altogether and replace them with a smaller feed-forward neural networks. It may seem like a downgrade because we have again came back from the RNNs to normal neural networks, but very surprisingly, their approach was way better compared to previous approaches in the paper that they show. And this changed a lot because now the model you can train this model in parallel. It's very easy. Like you can train all of these feedforward neural networks in parallel because they don't have dependency on each other. You first train all of them in parallel. You can do multiple GPUs or this kind of thing, like big server farms to train all of these networks in parallel. Then you have the state, and you again train those in. So I mean, you can't decoder and encoder in parallel, no, because that needs it, but all of them in parallel, then all of them in parallel. In two parallel steps, you can train the whole transformer network, right? And that was very helpful. So now you could, people saw that, oh, we could use very, very long text, very long corpora, and just throw a lot of GPUs to enable parallel computation and train them all together. And people have actually done this. And a pioneer actually here was OpenAI from 2020 or so, the GPT model that we will cover in the NLP week, what they actually did. That now is pretty famous. Everyone, we all do our assignments using GPT and everything, right? So this is a trend with the whole transformer architecture. And this helped to change a lot, not only in text, but also in images, because you can also input images here. It's not only limited to text. It can be time series, and it can also be images. Images are actually very interesting. We can see how we can turn images into a time series. Maybe I don't know if in the computer vision week, if they have time, they would cover vision transformers. So that's an idea on how we can think about images in this format. That's something different. That's on its own, and not only images, but people have also been doing audio and video as transformers. Like you can input everything here. You should just know some specific pre-processing techniques for each data type, and you can input everything here. You may have heard about multimodal models, like Omni model. They will just say, I think, something like Gemini. No, Gemini, yeah, Gemini is I think multimodal, and I have heard GPT-4o or these kind of fancy models. All of them are using the same thing. So this is a basic transformer that works like this. So we have the encoder and decoder. Inputs are here. We don't have RNNs. We have feed-forward neural networks only. We have the output states, and then we input everything to the decoder, allowing it to be trained in parallel. Any questions here? Yeah.
You have to train the attention before
So the whole encoder is trained all together with the backpropagation, including the matrices from the attention weighted sums, as well as the matrices inside the neural network. So the whole thing is here the input, and here are the losses, and the whole thing is in the same backpropagation. Yeah.
losses really come from here.
Well, yeah, you're right. But so yeah, this is the co-training approach. But what I was saying is that this can be done in parallel. The loss is not computed here. Loss is actually computed there, and there are also a lot of ways on what does loss mean specifically in text, because it's not very clear. Like, what does loss mean? We don't have the how we can evaluate the translation, because there are not about translation. I will cover about the whole loss thing and how you could train this in the NLP week. So yeah, training this usually very depends a lot on the task. So it's not very clear how you train the transformer model regarding the loss and what to optimize for. I'll give more ideas about that in the NLP week, and if also vision transformer they're covering, maybe in the vision week you will also see some. Yeah. What do you mean? Sorry. Oh, okay. You mean the downside of this whole approach? So one downside is that, okay, it depends on what you compare to. Are you comparing to RNN with attention or to simple RNNs? Here, the RNN with attention. Yeah. One main downside is that the positional encoding is totally lost. That's what I wanted to cover. So we have here no positional encoding. We don't like here, there's no information that says which word comes before each word. And this does not make a lot of sense, because in translation, the order of words, as you said, is important. Or in other tasks, like transformers are great is different from great are transformers. Like, there are two different sentences. And I can better example. If you swap R and transformers, it turns to a question: are transformers great? It's very different from transformers are great. So the idea is, yeah, you're right. Here we lose the positional information, because here this links somehow incorporated positional information inherently, because here the output is not only the exclamation mark, it transformers are great exclamation mark. So somehow the positional encoding was embedded into the model, but here we lose all of that because we have no direction like this. So we need to fix this. And the idea is, yeah, we add a positional encoding. I'll cover it in a second. How do we fix it? So yeah, perfect. So now that you know the general idea of transformer, let's explore how they are designed. Today, maybe I should have said this in the beginning, but today the focus is really let's understand what does this architecture do. Mostly, we'll also cover a code, but maybe more briefly, not like yesterday that we coded everything from the beginning ourselves. I will mostly go over the code, because I think it's very important to understand together what really this model does and how it is designed. Perfect. So what do we have here? This is the general thing that we just saw. So I mean, first format, I just picked another visualization from another website. So we have an input. It can be, I need the task that I'm doing all over this lecture is machine translation, but you can have a lot of tasks, right? It can even be time series, like prediction in time series, or in a time series, for example, weather forecast or anything. It's not limited to text. Don't think it's limited to text, but it's text because if you search on the internet, like I think 90% of usage of transformers now is for text, for textual data. But it doesn't mean that's only text. You know why that's it? Because usually in other time series tasks, the complexity is not enough that RNN make a problem. Usually also simple RNN and LSTMs work relatively well. But in text, because text is very multidimensional and we have a lot of words and translation is no easy task, even for humans, usually need to have more complex models. And that's why transformers are very helpful in the domain of text. Actually, they changed a lot in the domain of NLP and also vision. So yeah, we have the input sentence. It goes to the encoder, and then you can see there are multiple encoders here. I mean, I don't want to use the arrow here, but yeah. So this is the general transformer blocks. This is not. Uh, maybe this I should have said this. So these are not each of them. You may see why there are arrows here, but this is something different. So each encoder block has different cells for encoding each of the words. So this is one full encoder. And then you output the whole thing to another one full encoder step. And the transformer paper initially did it 6 times. This was just, they didn't have any reason behind doing it 6 times, but it worked well in practice. So it's not that they proved that 6 times is good, but so each of these is a full test. So it's a full encoder. You encode the whole sentence and then you do it 6 times to better capture the specific details in the text. This was the whole idea. And then you pass it into the decoder and you get the output. So all clear? Yeah. Oh, you mean the first encoder? So the idea is that it encodes several times to capture more details in the data. Oh yeah, because here, if we do this over time, maybe maybe they tested like this. I don't think they have a proof for this. They just saw it work during practice. But I think maybe the idea is that encoder detail would be lost after 6 rounds of decoding. I don't know. Maybe I'm just thinking they saw this work and they don't have. Also, I read their paper. They don't have many, from what I remember, they don't have many specific proofs or things behind what they did. It just works well in practice, so everyone is using it. It's mostly like this, from what I know. If anyone knows something more, tell me. But from what I know, it's mostly that, yeah, it works well in practice. Even the number 6, I think they explicitly said we just tried it and it worked. So why not more? Why not less? Yeah, you can try it more and less. But it worked well in practice. So yeah. So what does have the encoder here? The encoder and the decoder are each composed of several things. The encoder contains something called self-attention. This is a bit different from the simple attention. I mean, this is an attention, but on a certain way, done on a certain way that I will cover. And then we have a simple feed-forward network. This is the structure of each encoder. So these what green block is one of these blocks here. So we do a self-attention and the feed-forward network 6 times in the original transformer architecture. In the decoder, we again do a self-attention from the so self-attention. I'll talk about this, but imagine it's a type of attention. So self-attention is done on the input, right? Here we do a self-attention and the feed-forward network. Again, self-attention and the feed-forward network. Self-attention, feed-forward network, and to down. Here, each time we do a self-attention from the input, another attention from the encoder, right? And then the feed-forward network. What is the visual idea? So in the decoder, we have 2 layers of attention. One layer of attention is based on the decoder's previous decoders itself, and the other one is from the encoders. So what do they do here? Why do they do this like this? The encoder only takes the input, and that's enough. But the decoder at each step also attends to the previous things that were decoded. Why do they do this? Imagine in a text. Just to the end, if we want to encode and decode it, it would be translated to I am a student. If you write I am a, the model usually has they found the model has a better job to complete it with the student. It's very different. For example, there are 2 things. For example, I will tell you what is the 4th word in the translation of Visual Studio Studio. And the other question is that what is the word that comes after I am a in the translation of Visual Studio Studio? I'm sure the second one is easier for you because you already know the translation until now and you can easily complete it, given what was decoded until now and the original sentence. But if you have no idea on what was decoded before, it makes it harder for the model. So the decoder, as we said, is done autoregressively. What does it mean? It means that you decode word by word, and each decoded word has a role on what word would be decoded next. So when we want to decode each word, it not only sees the whole input sentence from the encoder, but also the previous decoded. So the model, when it wants to output students, it not only sees the whole sentence just to beyond, but also sees I am a. So it knows that it has already covered Geometry, so it should now translate it. So this is the whole idea. Decoding is done step by step. Maybe if you go to GPT and ask ChatGPT a question, you see that it outputs word one by one, right? It doesn't output the whole text at once. but rather it writes the text like a human, right? Like it's word by word, and that's because really it's done like this. So the whole first, when you send the sentence, the whole text question that you ask is encoded, but the decoding is done word by word. So that model is trained not on machine translation, but on question answering, which I will cover in the NLP week. So that's another task which is very difficult. Question answering that answers any question that you ask them. So the GPT is trained for question answering. GPT, I mean, the chat GPT is trained for question answering. And you ask the question, it first encodes it with the whole thing, and then decode it word by word. For example, if you ask it, what is your name? It first decodes I, then it again says, what is your name I, and decodes am. No, it again says, what is your name I am, and decodes, for example, GPT. So it's like this. Decodes word by word, given the word that it has decoded previously. This is the whole idea of the decoder. And as you can see, because of this, we have first not only attention to encoders, but also attention self-attention, as you call it, to also the decoder itself. So decoder attends to both itself and the encoder. But encoder, of course, can't attend to decoder because decoding has not been done, so it only attends to itself. Any questions until now? Right, perfect. Also in chat, if you have any questions, maybe you can just check regularly. Perfect. So, and this is okay. Here is also another enlarged version of the transformer encoder. So we have the input values here again on the board. We have the self-attention that I will cover it. And we also have the, okay, this is the output of the attention layer fed to feed-forward neural networks, and then the outputs are passed to the next layer. So it's very simple. It's just an enlarged version to show you how it happens. And also, this is another type of modeling the attentions here done on a transformer network. The previous picture that I showed you was done on an attention in RNA. Here is the transformer. And as you can see, this is very interesting because the animal didn't cross the street because it was too tired. And the idea is that it should attend to the word that it refers to. And model, without explicitly telling this, learned it. It's very interesting that when you train the transformer model, you don't train it to link each pronoun to its name, but the model inherently learns. Here it links it to the animal, as you can see, because the animal is the most highlighted one. So it somehow can follow which pronoun refers to what thing. And it's very interesting that in a scale, when you do it with very large models, this kind of behavior usually emerges without retraining for them. Like we don't train explicitly to do this, but this kind of behavior emerges. We will see a lot of more examples like this in the NLP week to see how this kind of behavior usually emerge in larger scale. But yeah, this is an example. So what's the self-attention? The self-attention, okay, is a type of attention, so it's inherently a type of weighted sum, but it's more fancy. So the authors of the papers leading to the transformer paper and the transformer paper itself did some modifications over time to change it from a very simple weighted sum to a fancier version of weighted sum that we will see now that is used in the transformers. So we don't just use a weighted sum in the attention phase of the transformer. It's a bit more complex that we will see now. Let's get a bit more technical from here. Until now, it was also technical, but here a bit more technical to see how attention specifically works in transformers, because it's a bit more complex than a simple weighted sum. So this is the whole self-attention process. I classified it into 4 steps. First, the algorithm or the code creates 3 vectors from each input of the encoder. So what's that? Here, embedding is the input. The word embedding is the NLP word. I'll cover it, but imagine embedding is an equivalent vector for each word. So you convert a word to a vector or an input to a vector, okay? So embedding is just the input. You create 3 vectors from each input. We call this vector queries, keys, and values. How you create this vector is easy. You just multiply this vector in a matrix, and you will have the vector in out. And these matrices are learned in the back propagation. So it's not anything that how we should find the matrix. It just you initialize it randomly usually, and it's trained in the back propagation. So you generate three vectors, query, key, and value for each input. We will cover what they need, but you generate three vectors. And as you can see here, the math methods are usually the height is more than the width. So these three vectors are usually smaller than the input vectors. This is, I don't know why it's done maybe for computational practices, but it works well in practice. So you somehow are also compressing them, not too much. It's not that you compress the whole vector into a single number, but you compress them a bit. So you convert them into three vectors, query, key, and value. Any questions until now? So this is the first step in how attention is done in transformers. It's fine. Then what you do here is the weighted something, but done in a more fancier way. For each input, we multiply its query with all the keys of the others. So for example, here, the sentence is thinking machine. I took it from a website, so this example picture. So you multiply the query here, Q1, to the keys of each word in the sequence, K1 and K2. So for example, here, you multiply Q1.K1 and Q1.K2. This is the inner product, right? Very, very simple. You just, or maybe 0.5 what? Like, no. Elements wise? I don't remember actually. What was this multiplication? But you multiply these two vectors. I should check if it was element wise or inner product. I don't remember actually, to be honest. But yeah, you somehow multiply these two vectors. The query of each word to the key of the rest. And you save the results as the score of each word. So this is somehow the score of each word. Perfect. Then you divide this score by the root of the dimension of the key vectors, usually. So this is to make the gradient computation more stable. It's a kind of normalization. You, for example, here the query, the key vector is like 3, so you divide it by SQRT of 3. But in practice, it's usually more than 3. But you do it. So you divide this, and then you put it into softmax. Okay, what is softmax? Here, I think we once said it, but we should say what is softmax. So until now, before I get to softmax, any question? Imagine softmax the function that we just apply for now. Yeah.
So this is not equal to what do you use? Not to the single video, that's a control.
So yeah, here embedding, you can have them separately. So you can have a model that converts each text to embeddings. And those embeddings can be trained separately by another task. It doesn't need to be trained in the same model. So you can have fields embeddings. Embeddings is just a translation for each word. So I mean, translation is not a good word. It's a mapping for each word to a vector, right? And the way you train it, you can train it in this process, or you can have pre-trained embeddings, which is not quite used a lot. I will cover the differences in the LLT week. What is embedding? How do you do it? And how do you pre-train it? How do you use them? I think maybe most of the morning actually we were talking about embeddings because it's very important on how do you embeddings. And actually having good embeddings is very useful for having good NLP models because embeddings can somehow have the semantics of the word. Like this is a vector equivalent to a word. But yeah, we'll cover it later in the week. No worries. I will talk a lot about embeddings. So, but yeah, apart from that, until now it was fine, right? So we multiplied the key, multiply here, multiplied queries with all the key, and then divided by the root of the dimension of the key vector. So here we have some scores. What we want to do is have probabilities. We have a method that is quite used a lot in machine learning and deep learning. Maybe you know already from your mathematical or something like this, that converts values, any values, to probabilities. The way that we do them is usually like this, done like this. The formula is that we calculate e to the numbers and divide it by the sum of e to the numbers. So e is the like exponential number, as you may know. For example, if you have two values, 2 and 3, the equivalent probabilities would be e to the 2 over e to the 2 plus e to the 3. And the other probability would be e to the 3 over e to the 2 plus e to the 3. I don't know if it was clear. Maybe I can write it. Where is this? Where the marker is here. Wait, right here? Oh, here. So what I meant is something like this. For example, we have two numbers, 2 and 3. Very simple. We want to convert them to probabilities, which are values between 0 and 1, and their sum is 1. Right? This is the differential probabilities. What we usually do is to apply the softmax function, by which we do this. We convert all of them to, we do them in e to the n. So it's like e to the 2 and e to the 3. And then we divide it by the sum. So it will be converted to e to the 2 over e to the 2 plus e to the 3. And the other number will be e to the 3 over e to the 2 plus e to the 3. So now both these numbers are between 0 and 1, obviously, because it's a like it's a division, and sum of them is obviously 1. So these are now converted to probabilities. This is one of the standard ways that many times in the machine learning and deep learning, we convert values which are not probabilities to probabilities. Can everyone see this, by the way? I think. All right. Okay. So let's go back. So this is the whole idea of softmax function. And here we also apply the softmax function here to convert these scores that we got to probabilities. This also helps a lot because you can convert very, very big number to a smaller number. It's very obvious, right? Because it's very helpful. You just do the very basic formula, you can convert, yeah. You can't, because e to everything is always positive, right? Yeah, you can. And it will work still. So any number here would work. And that's actually a point of, you may ask why we don't just divide it by the sum of them. Because if one of them is negative, it would not work. Right? But here even negative values work. So it's very versatile. Yeah. Yeah. So yeah, this is a fancier way of doing the weighted sum, you can imagine. This is how they do it in practice, because I mean, you may see it's very difficult to do all these vector multiplications, but in practice, it's also very speedy because you can convert them all into matrix multiplication, which GPUs are very good at. So also it helps. Yeah, in practice, it helps a lot because GPUs are very good at matrix multiplication, and that's why everyone is buying GPUs because they do matrix multiplication very well. So yeah. All right, let's go. You have to begin. So then we have the output of the softmax, and you can see when we do this, the values are probability 0.8 and 0.12, and the sum of them are 1. That's always the case because per the formula of the softmax, the output can never be negative, can never be more than 1, and it's always between 0 and 1. So, and the sum of them are always 1 because the formula, the denominator is always the sum of all denominators. So it's always very good. So here you just multiply the value vectors. Okay, okay. So you have the softmax values, and then what you do is that, okay, remember we had a value vector. Also, one of those 3 vectors are value. We haven't touched that until now. We multiply the value vectors by the softmax. The idea here is that we remove irrelevant values in order to be calculated the sum. So it's kind of weighting. Here is the weight part. Softmax are the weights. The softmax value are the weights, and we multiply them by values, which are a mapping and a representation of the embeddings, which themselves were a mapping of the input data. So somehow we weight the input values, and then we sum of them together. So this is the whole thing. So this is a fancier way of doing the weighted sum by having a division in there, which works at normalization, as well as the softmax function, which converts everything to probabilities and is proven to be useful in practice. So yeah, that's how they do it. Any question until now? How they do their ray of attention in transformers? Oh, sorry, something happened. Sorry, could you repeat again? Yeah, here. So
Is a values there or no?
So yeah, here to create them, you use three matrices. You multiply the embedding by these matrices, and these matrices are learned in the back propagation. Yeah. So you just initialize with some random matrix, and then they are learned in the back propagation.
And so here the dimensionality is the input value is 4, and the query is 3 to 12.
Exactly, 4 by 3 matrix. Yeah. I mean, in practice, they are much larger, but yeah. Yeah, for exactly. And usually it's like the dimension of query key value are less than embeddings. Because embeddings are very high dimensional, specifically in NLP, as we will see. And if we just pick those large dimensions, the model would never train, like, because of the big size. It would take years to train. So we just map them to a smaller dimension so that we can train. I don't know what I can check, but I think there's like maybe thousand millions or dimensions for embedding sometimes. So you can imagine they're very big in size. I should check maybe how much is the usual dimension of, for example, embedding in GPT. I don't know. I should check, but maybe millions is less. I have no idea, but I will check. So, all right. Perfect. So to recap, we created the three vectors by the matrices. We, for each input, multiplied the query with all the keys to access the scores. Then we normalize the scores by dividing them by the square root of the dimension of key vectors. We usually do this for having more stable optimization. Yes. Yeah. I mean, the number of elements in a vector. The very famous, like the normal definition of dimension. For example, here it's like, I mean, here in their example, I mean, here it shows 3 elements, but not that. It's usually more. So, yeah, exactly. So it's the dimension is the number of elements in a vector. Yeah. So yeah, so we have the queries key and values. We calculate the scores by multiplying query with other keys. Then we divide it. Then we divide it over the root of the dimension of the key vector. Then we apply the softmax function, which as we saw here, would convert all of the values to probabilities. Then these are the scores that we can multiply them by values. If we multiply the original score to the values may explode because the scores might be too high. For example, here the score is 112. And imagine the vector, maybe the values are already big. And if we multiply them by 112, they will be super big. So converting to softmax actually helps because there's always less than one and the values stay in a range. So we just multiply them, the value vectors in a softmax, and then we sum them all together to identify the output of the whole self-attention layer. So Z1, Z2 is a kingdom weighted sum of the X1 and X2. And the key parts here are the three matrices that were multiplied in X1 and X2 to form the query key and values. And those three matrices are learned in the backpropagation. All right. Anything to add? I think. Perfect. So yeah, this and also as we saw, there are matrices, but even better, you do not usually do like this in practice, that you do separate vectors and multiply them to find query key value and vectors and do all of this, but you can condense them together in a single matrix multiplication. Here, as you can see, you can put all embeddings into rows of a big matrix called X, and then just do 3 matrix multiplications. So it's way simpler than what we saw in practice, because GPUs are very good at matrix multiplication. So if you condense everything together in some small operations, it can work very well on GPUs. So here in the X matrix, each row is a embedding of a certain word. And then you multiply the whole thing and get a Q matrix, which each row is the query of a certain row, corresponds with the same row. So here we have 2 rows of X and 2 rows of Q. The first row of Q is the query of the first row of X. The second row of Q is the query of the second row of X, and so on. And also the key and values. And also the whole, if you condense the whole softmax and scoring part also in a matrix multiplication, you can do this. If you remember, we were actually multiplying queries to keys. So you can find it, you can consider it as multiplying the Q matrix with the transpose of the Q. So in transpose, you change the number of change the order of rows and values, and you do this so you can multiply, because otherwise you can multiply a 2 by 3 matrix here in another 2 by 3 matrix. You should do the transpose, and you divide it by sqrt of the dimension of the T vector. You apply the softmax. Here is a matrix softmax, which just means, yeah, you apply softmax to each row independently. It isn't anything more fancy. And you multiply it in the V matrix. So this is the matrix equivalent of the matrix. Why do we do this? Because GPUs are very good at matrix multiplication. So instead of doing them independently for each embedding, we do it in a single matrix also. And this is not also very simple because the matrices are very big, like the Q matrix, that KT is like very large, and the V matrix as well. So it's not very obvious, but it's still better than doing them independently because GPUs can parallelize or speed up the performance of doing matrix multiplications. So, all right, any questions? It's fine. Perfect. Let's make it even more complicated. So we can have multiple heads. What does that mean? Okay, you remember the Q, K, and V matrices, right? That were trained in the vector propagation. We can have several sets of Q, K, and V, and each of them work in parallel, individually, to generate different queries, keys, and values, and thus different attention scores. We call them usually multi-headed attention, and that's how it's also implemented in transformers. The idea behind this is that each of these heads or each of these sets of queries, keys, and values can help the model attend to different things. For example, one head can attend on the links between pronouns and their origin, as we saw in the it thing. One head can attend on when a sentence starts and when it ends. One head can attend on, for example, the matching between the gender of verb and the gender. I mean, verbs in English don't have gender, but in the languages that they have, the gender of the verb and the gender of the like noun of the sentence, or things like this. So different heads. I'm talking about text, right? In image is also similar. So different heads can attend to different things. By head, we mean a set of query key and value. So we don't only use one query key and value, but use several of them. And all of them are trained in backpropagation. And you may think, but how the model learns to learn different things in these heads? We are not instructing it to. And that's actually very amazing because the model does this without us instructing. So if you train a transformer, it would somehow automatically find different things to attend from different heads. And that's very exciting and one of the very magical things that's happening in the world somehow. So yeah, different heads of transformers attend to different things when you train them using a simple backpropagation. Any questions? Everyone understood the multiple head idea? So you just have the same QKV again another time, but with a different QKV. The only trick is that you should initialize them separately. You should not initialize them with one value because they would converge to one thing. Initialize them randomly with different things, and they would converge to different things. Yeah.
So these multiple heads, and it's like one level with encoding.
Yeah. Yeah.
Increment.
Yeah. Exactly.
So you do this maybe. Let's say there are 6.
Here in the self-attention, you can have multi-head self-attention.
So you've got 6 heads. This one.
No.
6 layers of.
Yeah, maybe 6, maybe more than or less than 6 heads. It's not fixed. I don't remember what transformer authors did.
6 is the magic number you thought.
Oh yeah, but here magic number for the number of encoders. Yeah.
So,
But yeah, a number of heads. Yeah, it would certainly be a number of heads. Exactly, a number of heads. Also number. I mean, also here they did 6, but other transformer architectures have done more or less as well. So yeah, this is the original paper. Okay. So very subtle. Okay, we have different heads. And yeah, this is also another visualization of the different heads. So we have each of the heads produce a different Z. That's what the output, right? Or we calculate attention separately. Here we have 8 heads in this example, and they calculate attention, I mean the whole weighted sum separately because the Q, K, and V matrices are different. But you can calculate them in parallel because they don't depend on each other. And this helps speed up the process a lot. If you have different GPU cores, for example, or things like this, you can calculate them in parallel. And that's why these server farms with a lot of cores are very useful, right? Yeah. Perfect. So this is yet another example of some multi-threaded visualization. I try to collect some visualizations that are nice to put here. So what is usually actually done in practice to even make it easier for the GPUs, you can concatenate all the attention heads together to do one very big matrix multiplication. I mean, I think it's obvious, right? Because if you concatenate two matrices together, you can do the matrix multiplication and do it like this. For example, if you have two matrices, you concatenate together and then you do multiplication, you can also separate the results based on the two matrices. So because it's usually how linear algebra works. It's very simple to do this kind of matrix multiplication by concatenating everything together so that the GPU can use its power better to do it as fast as they can. So yeah, just the idea that you can concatenate all of it, or yeah, you can just do it separately. It depends on what you want to do. The complexity of the code maybe is higher in this. I mean, PyTorch does everything, so we don't want to take care of that. But the complexity of the code might be higher, but it will. So, yeah, perfect. So let's go. We already covered this, but what is one problem with this approach? Remember what did I say? What is a main problem that we use when we go from RNN with attention to transformers?
Yeah.
The positions. Yeah, we lose the positions, right? So we somehow should add positional embedding, positional encodings. The idea is that to each embedding, we add another vector that is positional encoding. And these vectors are formed in different ways. There are two ways that we do it in practice. One is that you learn the positional encodings using the same backpropagation. You just put it as a matrix and you learn it. Or another idea is that you use a formula to calculate the positional encodings. And this one is actually used. Sometimes you can use, for example, formula using sinus or cosinus functions so that they have a periodicity as well, and that can help you introduce positional encodings. So this is how it works in practice, and I will also show you the code that does this. I think they still have time, so that's fine. So in any case, you will somehow create a positional encoding. Either you learn it via backprop or you do it from a fancy mathematical function. This positional encoding is unique per position. So T1 is unique per position first, T2 is unique per position two, and so on. You add them to the embedding, and then you give these outputs to the encoder. So the encoder does not have any idea of positional encoding. You do it before passing it to the encoder, right? So the whole positional encoding thing happens before you give your text to the encoder. So this is outside the transformer architecture, but you need to do this, yeah.
Like 0, 1, 2, 3, 4, 5, 6.
You can, but the idea is that the model should somehow know this, and this can also happen in the embeddings normally. So this, when you add this, the idea is that the new embedding is not an embedding on a different board, but it's something that the model can know what was the position from. So it should not be from the same space as the embeddings. This is the thing that I'll cover in the NLP lecture in particular, but embeddings have meanings. They are not just random set of numbers. Embeddings have meanings, and positional encoding should not be a thing that when added to embedding, it would just lead to a new word or another embedding. For example, you can add vectors together. Maybe if I add some number to the original, it would turn to be another pronoun in French, for example. We don't want that to happen. So we don't want this to be a valid embedding. We want this to be to the, for example, if someone who knows what we have done can really compose it to the word and the positional encoding. This is the idea. So the positional encoding that we add should be from a different type. This is the general idea, but as I said, you can just even don't care about it and let the model learn it, the best positional encoding it can learn itself. Just do it in matrix multiplication kind of thing here and let the backprop learn. Yeah. So this is the full encoder together. Positional, okay, we have the input, which is the embeddings. We have the positional encoding, which is done before inputting them to the model. These ones are, okay, this again called X1 and X2, but they are piece positional encoding. So the color is a bit different in visualization. we put in self-attention. We just saw what it does, like the key query and value vector. It can be multi-headed, so it gives us the values. Then we usually also do a layer norm. We saw how layer norm is done yesterday. What is that? In the transform architecture, we usually do also a layer norm just for normalization techniques. And then we have the feed-forward networks. We again have a normalization on the top, and this is the whole one encoder. We do this whole thing 6 times. We don't do positional encoding, I think, again, but we do the rest 6 times. So this is it. The whole this green box is encoder one. This is done 6 times. All right. Any questions here? I think the rest is fine, right? The important was self-attention. You already know layer norm is just a normalization on top of it. So, any question? And you can now easily guess how we can implement it in PyTorch. It should be very easy, right? It's just a sequential of an attention of layer norm and feed-forward network. We'll just see in the code actually. So it's not very complex. What about decoder? So the output of the last decoder, the last encoder, sorry, it's not very. I think it's less encoder, yeah. So the slide that we can run, but maybe let me start on picture a little easier. So we have the encoder. We had the embedding with conditional encoding. Here it's called the time signal, passed into here. And then we decode words one by one. The decoder attends to two things. First, it has self-attention on the decoder itself. So what does it mean? Like the previous words that were decoded. So when decoder wants to decode a word, it pays attention to I and am. So we have a self-attention running on this. After that, we also have an attention on the decoders, on the encoder, sorry. So we have 2 layers of attention in the decoder. It's not only one, but first it attends to the word that were decoded until now, and then it attends to the word in the encoder. We call it sometimes cross-attention because it's from the decoder to the encoder, right? So one is called self-attention and one is called cross-attention. They're the same thing, they're attention, but they attend to the different things. So encoder only attended on the input, but here we attend on the output and the encoder result. I think we can see an example here. So here is the thing. So output, I mean, here you may see why outputs are included to the model. I will talk about this in the NLP lecture. You can sometimes even input some outputs. This is something from the NLP. I will not enter it. So for now, ignore this. But yeah, you have the input embedding. You apply the positional encoding. You have the multi-headed attention, normalization, feed-forward normalization, and this is applied n times. For example, 6 times. This is the input. Then the output. So what the decoder does? First, there is an attention on the things that were decoded until now. Ignore mask for now. I will talk about what's mask. But yeah, it first attends to the decoder thing, then normalization, then attends to the encoder stuff, as we can see here, then normalization, then feed-forward normalization. This is how it's done. Right. So the decoder is quite similar to the encoder, but another attention is added because it not only needs to attend on the encoder, but also attend on what has been decoded until now. In the end, we have a simple linear and the softmax. Softmax, why we need softmax? Because we need probabilities. Like, for example, if this is the classification task, we need also softmax to convert values to probability. It's not a part of core transformer, it's just the output, but these two are part of the core transformer. And we also have several decoders. We don't only have one decoder, but we can have 6 of them or more. Or less. So one thing that I didn't say here is the mask word here. What is mask? So let me say like this. Imagine the same sentence, je suis parsa. I want to translate it to I am parsa. When are you decoding it? For example, now imagine you are on the word parsa. You want to decode that. You have already decoded I am, but you have not decoded my name yet. But there is some value in the last cell. Maybe it's a null value, but anything. We don't want the model to attend on that at all, or to get full or anything like this. You may think, but the model would learn it automatically, but we would see in NLP that it's not always the case. So the thing is here, we do some modification to the attention, and we explicitly zero out the attention to the words that have not been generated yet. So those attentions are explicitly set to 0. There is a slight modification in the attention phase. We only attend to the words that have been decoded until now. That's the meaning of mask. We will talk about masking, I think, a bit more in the NLPV because it's so important also when we are decoding text. But yeah, so this is the general idea. Mask means only attend until what has been generated until now, because it doesn't make sense otherwise. All right? Anyone understood the mask thing? Perfect. So we're wrapping up the slides because we want to get into the code. Let's see what did they achieve. I mean, this is the a comparison in the Transformers paper. So from Google, I think the link is maybe wrong, but yeah, I think from Google. I don't know. Maybe I think it's from Google blog post. I'll fix it. So what did they achieve? Here is a translation, two translation tasks, English, German, English, French. This is the RNN. This is the CNN. Somehow, even the CNN, because the CNN were newer, I think, working are better, but Transformer was much better. So as you can see here, in both tasks, Transformer beats the CNNs that they tried, as well as RNNs in their task. This maybe this is not a very big difference, but in practice, after people got to use Transformers, they did several modifications to it, which we'll cover in the LPV. More interestingly, two main groups tried to remove encoder at all, only have a decoder only transformer, and another group of researchers tried to remove decoder at all and only have an encoder only transformer. And actually, that both turned out to be very, very useful. You may have heard of BERT, I don't know. So BERT and similar models where I will cover it in the LPV, where models that only have the encoder and remove the decoder completely. And they are also very useful. I'll tell you why they are useful and for what task. And also, you all know a very famous example of a decoder-only transformer, which is GPT. GPT is a decoder-only transformer. They remove the encoder altogether. You may think, but how does it make sense? Because we input something and it should encode, right? But I will talk how they did this and what benefits it came from. It's purely NLP thing, so it's not really useful for other tasks, but just wanted to let you know that you can remove encoder and decoder as well, or do a lot of modifications to a transformer architecture. And this was actually very early. Blue is the metric for translation of 28 is now I think nothing. So people have been beating the state of the art almost in all NLP and also computer vision tasks with I think with transformers. So this has been very nice. Perfect. So any questions until now? We can see example code together, but if any questions from the transformer, yeah. Okay. Yeah, maybe. Okay. Okay. Yeah. So V1 and V2 are both generated from Q1. So all vectors generated from the query of the one port are summed to form the set of them. So yeah, the query is the set. So here V1 and V2 are both have the in their formula. I mean V1 and V2 is actually misleading because these values here, these two here are actually V1 and software. Yeah. So these two vectors are generated somehow from the Q1. Both. So they sum them up to form the. Yeah. Perfect. Anything else? All right. So okay, let's see it on code together. So I'm using okay here I'm not using self-written code. So there is a nice GitHub repo with a full implementation of transformers for time series data. I really like the code from what I saw. So we want to just cover a specific. Here we are going over code because I don't think we have time to write code from scratch ourselves from the time that we have because transformers are also a bit complex. So we would just go over a code and we'll see together how it works and how also you can apply them to your specific task that you want. So it's a very simple time series task that we are covering the code. Also, I can send a link. Let me first. Okay. Um, I'll send the link later to you. Oh, sorry. Okay, perfect. So let's cover the code. This is the let me send it. Sorry, I can't find it. Hmm. Maybe it comes if I search. I can't find it now. Give me some seconds to see if I can find the code. Where it was. Okay, no worries. I'll send you the code later, but for now we'll just go over the code because I think it's easier. So yeah, here's a example of basic code that's makes a simple transformer model. We'll go over this code step by step to see how we can code our transformers. So here, first of all, we need to generate data. Okay, you can have some time series data. In this code, here they're generating synthetic data. So you can just generate your own data so that you just a simple sinusoidal data plus some random noises added to the data. You can see, right? This is a very simple sinus wave plus a normal with a mean of 0 and a standard deviation of 0.1. So they're just a set of data and they're just saving it. So you can ideally, if you want to use the same code, you can just replace here with loading your own data from any time series festival that you have, and you can reuse the same code. So what do they have here? This is how they define the model. So first of all, as we said, you need to define the positional encoding before we get to the real transformers. Because we need to have because we need to because transformers by nature doesn't include positional encoding, and we input text to it. It would not make sense a lot because imagine the texts are shuffled. You can't understand a lot of things for them, and the encoder and decoder would not be successful. Also in time series. So we need positional encoding to add positions to every entry in the data. So as you can see here, they define positional encoding as a very simple, also PyTorch module. You can also do it as a function, but it's also simpler to do it all at once so that PyTorch learns to do everything. As you can see here, they added dropout layer. I don't know if we have covered dropout here yet or if it was in the not, but dropout is actually what does it mean? Is that you randomly remove some connections with a certain probability. The idea is that this would help model generalize better and not to overfit. It has been shown that it's sometimes useful in practice. You just randomly, with a certain probability, remove some of the connections in your network to avoid overfitting. And surprisingly, it may seem counterintuitive, but it has been shown to sometimes be useful. But you usually do it with a very small probability. So yeah, so during training you do this, and then you need to scale your values during inference to account for this loss, but it will be automatically done by parser setting. Yeah. So you just the dropout by removing the connections is obviously during training, so that the weights are not learned for that connections. Yeah. Okay, and here they do a combination of an exponential and a sinusoidal and cosinusoidal wave. So this is the way, actually, it's the complex way that you do positional encoding. Instead of this, you can just use a feed-forward network and let PyTorch learn it for itself, learn the positional encoding for itself. This is also another alternative that some people can do with modifications. But here they do the sinusoidal and cosinusoidal way of positional encoding that I told you. Because, for every position, the value of sinus would be somehow unique in a period. And so this is how they do it. Like there are also formula proving why this way is useful, how this works, and this kind of things. I don't even know myself, but you can also check it out if you want about how positional encoding with sinus cosinus stuff. And the forward, you just add the positional encoding from the arrays that was saved here. And here also they apply the dropouts, but it's not like super necessary. It's not in the original transformer core, so you can remove the dropout, but they just added it so that it helps with generalization. So this is the positional encoding. You do the sinusoidal and cosinusoidal, you can just reuse the same thing. Here comes the exciting thing, the transformer. Here they call it transformer with PE. PE is positional encoding. So it's like the positional encoding enabled version of transformer. And okay, here what do we give to the class? The dimension of the input data, dimension of output data, the dimension of the embeddings, the number of heads. The number of heads is again saying the number of different sets of query key values. So you can have multiple heads in a simple encoder. And the number of layers. The layers are here, the number of layers. Like heads are inside each layer, and we also have several layers. So this is the thing. And here they use the same number for encoder and decoder layers, by the way. So, for example, if you have 6 encoder layers, you also have 6 decoder layers. Here they're using the same number, but yeah. So, and you have also a number of heads as well. So what do they do here? First, they apply the positional encoding. So this is the init that they define the models that they want to use in the forward pass. First of all, the positional encoding is applied before anything else. Then they convert their input to embeddings. Here, because they are simple numbers and sinusoidal, you can just use a simple linear model. But in NLP, this doesn't usually work. So you need fancier ways to create convert words to embeddings. But here, just a simple neural network, just a simple feed-forward network can convert the input values of the time series to embedding. Also for the decoder, you do the same thing. Any questions until now? Fine. And the output layer, you also define the output layer, which again is a feed-forward network, if you remember in the slide I showed to you. Then you define the transformer. Okay, here it's very easy. You don't need to even define the inside of the transformer because the PyTorch does a lot of things for you. So PyTorch has a transformer module that you define the number of heads with the parameter n head, number of encoder layers and decoder layers. As I said, it could be different. Here in this example, it's the same because it just inputs here, but ideally they could be different. There's no reason that I think they would be the same. There's also a parameter called the model. This is the actual dimension of the embeddings that we pass into the model. PyTorch calls it the model, so just remember. And the batch first you remember from yesterday, it's the same thing that we had in RNN. The same thing that we had in RNN. So yeah, this is how a transformer with P is defined. You first do the positional encoding. We define the function that convert our data to embeddings, which, as I said, in NLP, it's a bit more complex that we will cover. You don't do this usually, but in simple time series data, you can do. There's the output layer and also the simple transformer. You define it from torch.nn that gets the number of heads, number of encoder layers, decoder layers, the dimension of the embedding. And in the forward, it's very simple. So what you do is you first embed the values, and then you apply the positional encoding. Remember, always you apply the positional encoding on the embeddings. You never apply it on the original data. So the first ever thing is to convert everything to embeddings. Then you apply the positional encoding, and then the whole transformer starts. So this, they should not swap them. First, always the embedding, and then the positional encoding. Then here's the masking thing. PyTorch has something for masking already that you can just use. That we talked about masking actually, and then you do the embedding on. Okay, here you don't use the masker yet, but you'll do it later. So yeah, here I think maybe they should have moved this here because it's more obvious. Maybe let's move this here because it's more clear. Okay, yeah. So first you do the encoder embedding and positional encoding of that. Then you do the decoder embeddings and again positional encoding. Then you want to define the transformer. So you give the encoder embeddings with positional encoding, decoder embeddings with positional encoding, and the mask. The mask is needed. That the transformer uses it. The PyTorch transformer uses it in the decoding phase because encoder doesn't need a masking, but decoder needs it, and you define it like this. And finally, there's the output layer, which was here, a simple linear model, right? You finally do the output layer, which is the simple feed forward on the top, and that's it. And-
What is source and
Yeah, source here, they define it here. So SRC and TGT are the embeddings with positional encoding for encoder and decoder respectively. So yeah, SRC is the embeddings with positional encoding for encoder. TGT here in their variable names is the encoding is the sorry embeddings with positional encoder for decoder. Okay, we will not like this. So here, SRC is equal to embeddings for the encoder, also with positional encoding added. So this positional encoding has nothing to do with encoder. It's a name that is a positional encoding. Positional encoding just means add the positions. It doesn't have anything to do with the encoder. And TGT is embedding for the decoder, also with positional encoding.
so what's where they come from?
Oh, from the data. What do you mean? So the SRC, initially SRC is just a torch tensor, which is just the input data,
If my
the time series. Yeah.
it's a time series, and the only thing is, okay, so it's the time series plus one.
Yeah, okay, if you have the time series, you should convert it to an embeddings because because transformer accepts embeddings, right?
But before that, so where is that coming from? Like, understand the.
Okay, let me write it on the board so that it's here. I can.
With the classification task, I have the output, I know what I'm looking for, but with.
Oh yeah, okay, but here we're not about output. So okay, here's the full transformer. Or maybe I'll write here so that people on the Zoom can see. So here's the full transformer. You have your time series data 1, 2, 3, like 4, 6.5, and so on. Like this is the time series. We're not talking about the text even, like numbers. This model, what it wants is some encoding with positional embeddings. So you first convert them to encodings, to embeddings. You first convert them to embeddings. So embeddings are some values, these are embeddings. These are just a transformed version of the numbers. You can just use a simple network here, a simple feed-forward network. In NLP, no, you need advanced way to do this. But in normal time series, just use a simple network. Then you add positional encoding, and then you pass it into transformers.
So that's the source, or that's the.
Yeah, this is the SRC in output,
Okay,
the final SRC in output.
good. So I was guessing that all along.
Yeah. So yeah, here actually the code changes the SRC if you see here, right? So it gets an input at SRC and then SRC equals f of SRC. So here SRC, but it applied these steps, finally this is the SRC. And also for the decoder, this is the TDT. And then it passes to the transformer.
If you lost, so target is really also the input.
This is the input from here. Yeah, a different set of inputs.
Different set of inputs or different set of transformation.
Yeah. I guess what you're lost about. So yeah, these are not the time series inputs. These are the outputs that are generated. You remember in the sequence masking, we wanted to predict the next number. We did, for example, okay, this was the window and we wanted to predict 5, and this was the 4 window output.
Yeah.
That's the case, right? In each step, the things that are generated from the decoder are actually used, right? So it actually one slice window later. The same thing in RNN. So actually the thing that RNN did was got 1, 2, 3, 4, and then gave us 2, 3, 4, 5. But we only took care of this final number because the rest were not important for us. But effectively, if you remember, the window sizes were 4 in both steps. Here, this is the same thing, but here, this is the input, the initial SRC that becomes the final SRC, and here is the initial TJT that becomes the final TJT. Yeah, sorry if I didn't explain it correct, right? Perfect. All right. Okay. So, any questions? Anyone? We are also getting to the end of time, but it's okay because the code is also near the end. All right. Perfect. So what do we have here? Here is running the inference of the model. and actually a bit similar to what you said. So here they are zeroing the output to initialize the model, and each time they are generating a new entry and adding them to the output. So the output is added over time. So the inference of transformer models to sequence model is always like this. You do one output at a time, one token at a time, and you add them together, as you can see in this code. So in a loop, first of all, the first output is there, and then you add each output of the generation of the model, or output of the forward generation of the model, right? You add each output again to the output array, and you pass it again to the model. You can see how it's done here. Because generations are done token by token. For example, if you want to translate just to parser to I am parser, first I is generated, then am is generated, and then parser is generated, right? And each step, the model also sees the previous generations. So here, first the output is the first word, and then it's passed to the forward. For example, here it generates am, and then am is added to the output array. So the next time the model sees I am. Is it? It's all fine?
So when you just bring with it, just want to predict the sets, what do you give to the books?
You can just give an initial value. It depends on the task and more. For example, in many LLMs or NLP tasks, usually have a start token that you usually give it the start, and then it will predict the rest for you. So usually give an initial token.
Which just one.
Sorry.
Just one token.
Yeah. You can just one token, and it will generate the rest of the token itself. So you provide one thing here, and it would like start generating token by token and adds back to the data that is sent into the decoder. So it generates the next token and next token. All right. And we will see a very specific example of this in the NLP week as well. So really how GPT will also like this, right? Or many other transformer models. So what do you do is that? What do you do is that imagine it's an autocomplete model, like you say, how, and then the model gets it and predicts the next most possible word from the whole thing. So it outputs R. Then then it adds R, and then they predict the most possible word. So the next is U, and it continues like that. So this is the decoding phase. In each part, here the exact loop that you see here. So for example, here, how R is this output here, it passed to the forward. The output is U. U is added back to the output. And the next step, how R U is sent to the forward, right? So the sentence or the time series or anything is concatenated over time to be more complete and complex. You may ask, when does it end? Either you have a fixed number of tokens to generate, or you usually end with a specific ending token. So whenever an end token is generated, you end generation. We will cover it in the NLP week, how usually you end the generation. Any questions? I know it's a bit more complex and a lot of things to understand, but we will also cover a specific example in the NLP week and train it together so that we can know. And by the way, so this was the model. One thing left here is, okay, how do you call this model? It's very simple. The training loop is quite similar to what we saw, but anyway, let's see. So you extract the sequences. There is a util function, load and partition data, just split into sequences. What we also saw yesterday, you just loop and split into sequences. Nothing fancy here. You can read the code later if you want. It's very simple, right? You just split the sequences. You split them into training and test sets. You use the torch data loader as we saw yesterday. Here also you saw, I think, the device because Peter was telling you. So because transformers and the model that we see also in the upcoming weeks are usually very complex, you can do them on CPU because CPU takes a long time. Usually move down to the GPU. So with this line, you can find the device that the model could run to. CUDA usually means GPU in devices that use, I think, NVIDIA chips, right? NVIDIA, right? Yeah, NVIDIA chips. So if your GPU chip is different, you should use different thing here. For example, in Mac, you should do something different. I think you should use MPS for Mac chipset because they don't have NVIDIA chips, but the general idea is the same. So you use the name of your GPU, and you can also check if GPU is available or not. It's very simple. Because you may be in some environment that GPU is not available, like in the server or anything. Then you just initialize the transformer that we defined. The optimizer, they're just using an atom with a learning rate that they defined here, 0.001. And the loss is the mean square error here. But as I said, the loss has a topic on its own. How do we define loss in transformers? Here is very simple, but we will cover specifically about this in the NLP week. So you just move in epochs. Number of epochs here, I think, is how many? 100. So just to let you know, usually we don't train transformers for example, 1,000 epochs. I have not seen that a lot because they take a long time, and usually with a less number of epochs, they work well. So this is something to know. Like if I'll come to fine tuning, may not cover it now, but I think 100 should be enough for this test, I assume. So here you just do the zero grad. Here the move to device is the place that moves the tensor to the GPU so that it can run faster. And here is the thing that you already know. Criterion is actually here the loss. They define it as criterion with the same thing. So you predict using the model, you do the loss, and then do the backward step and the optimizer. It's very the optimizer step. It's the very simple training loop that we also have seen previously. And then you print it. So then you go to the evaluation. Again, you use vtorch.nograd that we saw yesterday. We go to the testing batches. We again move them to GPU so that testing also done fast. Inference the model, loss. Then we use the infer function as we just saw that were defined. And here also they do a visualization. Yeah. And then you can print the evaluation loss on the test set and things like this. So I run this code previously because it takes a super long time to run. I run this here that you can see the results maybe. I think in Zoom it's not visible, right? But I hope you can see it now. So yeah, I just run this code, and as you can see, the loss is decreasing. So until a point, it's decreasing very good, but after a point, it's like all of them are close to each other, and even you have increases in loss. It means that somehow it is flattened. So if you use early stopping, as you may remember, it might have been ever more helpful. So it says that, yeah, as you can see, 100 epochs is not a lot here. It's a lot here, actually. You can do it very well with even less number. But in the end, we achieve a very, also a small loss on the test set, quite similar to the small loss we had on training set, which means that model worked well. I mean, the visualization somehow didn't show when I run it, and I don't want to run it again because the Colab thing also has a limited GPU, so it got disconnected. And yeah, but you can run it. I don't know if you have used Colab. How many of you have? Did you introduce Colab? Yeah. No. So Colab, if you want to use, is a tool by Google, colab.research.google.com. It's a very interesting tool that gives you a Jupyter notebook online, so you can run machine learning or deep learning stuff in it, and it also gives you GPU, but limited. So the free GPU is limited. Yeah, something like that. Yeah, exactly. And also, I think the very good GPUs are also paid. I think also depend on the GPU. I think it's enough. Yeah, exactly. So you can just open Colab, just create a new document. It's quite the UI quite similar to Google Docs and very simple. Go to runtime, change runtime type. Here you can choose between CPU and GPU. Like these GPUs are blank, but yeah. And also, okay, Python, choose Python 3. We don't want R. And for the accelerator, default is CPU, but use GPU. And then you can just run the code. But yeah, there are downsides, for example, that if you have it running for itself, or if you have a limit, you do it a lot, then you can't access the GPU anymore. And you'll be blocked until the time, unless you pay. But it's a good thing for testing if you don't want to put pressure on your laptop or its GPU. Oh, yeah. I don't remember actually the numbers, but yeah.
One thing is that on Kaggle, your session runs only for 12 hours. So even though we have 20 hours of GPU per week, you can't run more than the
I see. Yeah.
So remember we wanted to provide some projects. That with some pieces and program show you example with your game scroll up.
Yeah, I just run this because I didn't want to, because my laptop, it was a CUDA code and it was also a bit difficult to move it on Mac GPU. And also I didn't want to put pressure on the laptop, so I just ran it on Colab. And yeah, it didn't also take a long time, I think. I don't know if it's right. How much time did it take? Not now. I think if you are not disconnected, it would say how much time it would run, but not now. But anyways, yeah. So yeah, that's it. Any questions? I mean, this was a introduction. I know there's a lot of questions for you, but in practice, when we go to downstream tasks, vision and NLP, you will have a better idea on how this model is really applied. I mean, this is a bit artificial task, but if we like finally train a classification model ourselves that like classifies our text or things like this, you can really see how transformer shines there. Yeah, here is random data. Yeah. I mean, it's not random. It's a sinus plus some random noise. So it has a pattern. I don't know if you can visualize it, but yeah. Yeah, this was the data generation. It was not totally random, so it is a sinus plus a small random noise, a mean of 0 and a standard deviation of 0.1. So it's not a random. Yeah, it has a pattern, but it's not a perfect sinus. Because perfect should be too easy, right? But here we want also have some noise so that the model can find still it has the pattern. So yeah, and transformer is very successful at this task. Yeah. All right. Any questions? And also the time is up. Time for lunch. Thank you everyone again.